Hey guys, we are recording this session and we will resume what we discussed the last time and extend beyond that. So the thing that we were covering the other day were this example that we went through about in the exercise here, in which what we really did was attempted to extend this model, which was a simple linear model like here that we used, linear regression. And we modified that to try another learning algorithm, which was the k nearest neighbors, KNN. It's actually a very simple algorithm, as you know. It just takes three nearest neighbors, or any n, rather k nearest neighbors, and tries to estimate based on what those number of neighbors are and what the values corresponding to those values would be, and comes up with a result. That is what the selection of a different model involves. Basically, you use the library for the code that we are using. In this example, it is the scikit-learn library, and we select a different algorithm. It's as simple as that, just changing the algorithm. So all these libraries are already implemented for us. So that's the benefit of using ready-made libraries in open source. So what we essentially did is we took a look at the data, we selected a model, we trained the model, and we got some inference. We can call it, inference, you can call it prediction, you can call it estimation, projection, prediction, whatever words that appropriate to the data at hand. That's what we essentially try to do, is that we have some data on a two-dimensional plane, whatever the data points are, we try to fit some pattern and try to make a guess, estimate, prediction, projection, inference, you name it. So that's what essentially is for the given value of x, what should be the value of y. That's the whole idea behind all this fitting of various models and all that. That essentially we do that by reducing what is known as a error. So we reduce the error or we maximize utility. One of those two, either maximize this function or reduce that function. Some people call this function as loss function. And so basically the different names are the same thing. We are trying to minimize the error, minimize the loss, increase the utility, increase the benefit, and get to this point, which will give us an estimation of the value y. And we want to have this value y as close to what is mathematically possible given other existing data that we might have. So that's the core idea. And with that understanding, we will now finish off this first chapter and jump to a comprehensive end-to-end exercise, which is what the second chapter entails, which actually gives you a real-life experience of a real project, as described, but walks you through end-to-end from a pipeline perspective, a data pipeline perspective, to where the data comes from and what you do with what you produce as an output, and how does it go into the big picture in your company, in your whatever you're dealing with for your business. So that's the next chapter coming up right soon. Before we get to that, a couple of things: bad algorithm and bad data. These are the two basic things that can go wrong. So we can select something like a bad model, and then the algorithm is not the right model. That can go wrong. Or we have bad data, just the sample of data that we have collected over time. Some of it may be bad, most of it may be bad, or not bad. So depending on whatever you have, that's the classic challenges. Now, if you don't have too much data, meaning very little data, then it is actually hard to come up with the right set of prediction or inference or a number for the value y, that output that we want. That is hard to come by, because if you don't have enough data, that's one problem. When you don't have enough data to represent the problem at hand, the issue that you likely run into is noise. When you don't have good enough amount of data, then whatever data that you don't have will lead to sample noise, because your lack of insufficient sample quantity, that generates noise, and that leads to bad decision making because of this problem. And so the idea here that we have is this concept of unreasonable effectiveness of data. And that is a paper written by, something is wrong with my mouse movements. So let me just erase this. See if I can erase it properly. No. Yeah, this is not behaving properly. So what I will do is I'll switch over my PDF editor to another one and open that one. That should bring up a good quality editor. And this is where we were. So we have the book again. So I have basically the same book in multiple different software that I am currently using to account for my handwriting right in the book itself, so that we can keep track of what we discuss and all that. So here is the book that I think I was using the last time. So I just tried to use a different software and it didn't work out. So now we are back to the software that I was using the other day, which was this software on this piece of software, which is called Notability. So we are talking about bad algorithm, bad data. And so bad data can basically lead to sample noise if you don't have enough data. And the paper that, in 2001, Microsoft researchers, these guys, published is what is generally known as unreasonable effectiveness of data. Meaning if you have just very good quality, lot of data, having that is actually pretty darn good. And even a regular mainstream algorithm that is already known, without fine-tuning it too much, you can get decent results from predictions or inferences or intelligent guesses that you want to make. And so mathematically, or rather graphically, representing this concept as described in the paper, if you look at this picture, what you're really looking at is the importance of data versus algorithms. So on one hand, we have millions of words on one axis and accuracy of test, like how accurate the results can be. The accuracy it becomes really high, especially as the number of records that you have, the number of data points you have grows to millions of counts. The idea is that any of these algorithms will typically lead us to a decent result, really high accuracy numbers, close to like 95 and higher %. So that's the kind of result that you see when you have a lot of data and a lot of good data. And so that's the unreasonable effectiveness of data. Now, it doesn't mean that we discount the fact that bad algorithms can be disastrous. They can also cause disaster if you chose the wrong algorithm. Like, for example, when the data does not have a linearity pattern and you end up selecting the linear model, it's going to definitely lead to a wrong answer. And an example of that would be like, if you are estimating something like, I throw a stone in that direction with a certain amount of force. The stone obviously will go like this and then land at that point. And so you're trying to estimate how much distance will it go if I throw at a certain velocity at that angle, say 45 degrees. And so it'll land at that location, the range of throw that you might have. And so if you increase the velocity, the range may be more. Or double prime as opposed to single primes. If you throw it at a higher velocity, it might reach a bigger distance. Now that linear relationship is not necessarily linear. And, there may be other forces acting, like the gravity, for example. And so the idea behind this math underneath, which is actually not linear, when you really think about the bigger picture, when you have, let's say, the Earth, and then you try to throw a projectile. Now this time you're actually throwing a rocket as opposed to throwing a stone by hand. And that rocket will, have other nonlinearity in the underlying math come into play. For example, the concept of gravitational pull, and how much you throw and whether it is more than escape velocity or not. Those mathematical perspectives come into play, and definitely the idea is not linear anymore. So if you're talking about something that is inherently not linear and you try to apply a linear model, you will get wrong answers. That is understood. So I'm not discounting algorithms as such, but the research here basically tries to point to the fact that data is actually very, very effective to have. If you have lots of data, lots of good data, you can get by with just about most of the algorithms that will fit the pattern that you expect to see. And that's the research published here and visually described here. So the trade-off between, either you can work on developing data, which is possibly easier, compared to developing new algorithms might take time, might need research, might need something else that you may not be able to control. Whereas, getting data is potentially relatively easy. It actually also is hard. And when we talk about acquiring new data points, we are not just talking about getting data, but what we are really talking about is getting labeled data. That labeled data is actually expensive, really expensive. And I'll give you that example that I think I gave early on, which is the agate example. I go to the beach, I find that there are stones, so I say, take my camera, take pictures, and then I bring the pictures home of these stones that I find. And I know I can tell by looking at the picture that it is a stone or an agate. So I need to have picture 1, picture 2, and all these hundreds and thousands of pictures that I collect, picture N. These guys need to have a label. The label will be agate or not, agate or not. That labeling has to be done, and only then this data becomes useful. So that's the idea behind data. It's not just data. I mean, not just pictures, but it has to have a meaning to it, like some labeling, or rather, so not some labeling, precise labeling is necessary, and that is an input to the entire machine learning process, the pipeline. We need to have data which has labels, so we can tell what it is from a data point, and then we can, of course, use the data to make predictions, and of course use algorithms. So the trade-off here inherent is the actual thing you will run into. Most companies, most businesses will focus their energy here because they might have data. They just want to use an existing algorithm. But some of the companies who are on the cutting edge may want to actually research and may refine the algorithm used. But most of it is actually in the process of using data accurately. And that is an art. It's not just science. It is also an art. So we'll see how that data and how will we use that in terms of applying an end-to-end pipeline of data from a real example as coming up soon. Now, in this picture that you're looking at, in the graph here, what you're looking at is non-representative data. So the data that doesn't actually fit into the overall picture. Like, we can, of course, look at a variety of things. For example, look at this line here, solid line, this one versus the dotted line here. So there are two different lines that can be potentially drawn on the model that we have, on the data point that we have, because of what the data representation looks like. Now, if you look at the red versus the blue dots, so these are blue dots here, and some of these are red. So these red dots, if you look at them, if you include the red dots, the line kind of changes to this solid line. If you exclude the red dots and just go with the blue, you will find that the dotted line fits better. And so if you actually put a linear model, you might get either this line or that line, depending on which data points would you account for, and if some of them are missing, things of that nature. That is likely to happen. That's where you see that if you don't have the red items, it might lead you to this line. And in such cases, what you're looking at is a sampling bias when you don't have representative data. So the idea is to use a training set that is representative of the cases you want to generalize to. So if you generalize using the blue dots and you don't have the red dots available to you, then you end up with a dashed line, which is not the correct generalization, because it will actually produce wrong results for countries like Norway, Switzerland, Luxembourg, and things like that. And that is the idea underneath the concept called sampling bias. Now, sampling bias, there is a famous example from history, and that was an election example in 1936. Now, I was not, none of us, this is just a historical example, but we know from history that the digest, that agency that conducted a survey, they sent a poll to 10 million people. And what happened was that they got an answer back, and they predicted with confidence, high confidence, that Landon would win. That was the prediction. But actually, Roosevelt won. the reason underlying the bad sampling, or rather the sampling bias, comes into play. Let's see what is going on under the hood as to why the prediction was this and the actual result was different. You can actually apply the concept of sampling bias right here, because the guys from Literary Digest that took a poll of 10 million people actually obtained the addresses from telephone directories. That is a wrong source to pick and go and poll. They're looking at telephone directories and magazine subscribers and club memberships and things of that nature. These people who have, or rather in 1936, who had a phone or are subscribing to magazines or are members in the club, typically are rich people. So you are sampling the rich, and they are likely to vote, Republican. That's the assumption, and that's the reason why the actual poll results was Landon win. That was the prediction. However, the data that was chosen as the basis for the poll had a bias built in. The bias was, these are rich people who have money, who have phones, who have magazine subscriptions, who have club memberships, and that they just took that list and just sent out a survey, and they're basically got a result that was biased to begin with. And that's the idea underneath of sampling bias. And so less than 25% of the people who received the poll answered. So this also introduces a bias, which is you're not actually getting answers from the people you sample from, and they're ruling out people who don't care. Like people who don't care don't bother to vote either, and don't bother to even respond to a poll, and so they just don't care, and so you're ignoring them. Also, this is also a different type of bias called no response bias, meaning you poll them but they don't respond, and so you just assume based on whatever that response that you don't receive, and that is a no response bias, and that is also a problem. And in the recent elections, like we had Clinton, Trump. Now I don't have the basis of what this agency, what is the agency that actually does predictions. There is this agency called 485 Election Prediction 2018. So you can see the predictions of the people who are in the business of making predictions these days, and that is this company. Actually, the Nate Silver is the guy who does it. So Nate Silver. This person is a statistician, and what he does on his website here, Nate Silver, is that he scientifically tries to get an estimate of what would be the prediction of a particular thing that he was focused on 2016 election predictions, and he kind of predicted, and we know what happened. We know what ended up happening. Now we have Donald Trump as the president versus the other lady, Clinton. So the predictions were like, Clinton will win was the prediction, but again, I don't know the basis, so I cannot actually make a claim that Nate's data set was sample bias. I cannot say that because I don't exactly have the sources that he used to come up with the predictions that was generated in the last presidential election by this gentleman, who, by the way, I am hearing that he has revised his methods of making predictions, and he's studying it further as to what is going on, what caused the prediction to be wrong. So I don't have exact data from him to make a comment, but maybe it's a good idea to just keep an eye on what this guy does for future elections. So you can just, if you're interested, not necessary, but is a person who does these kind of things in terms of predictions these days, as opposed to Literary Digest, which I don't think, maybe it exists. I just don't know about Literary Digest. But having said, we are focusing on understanding what sampling bias is, which we did. So moving on, poor quality data, if the data itself is bad, for example, if you're trying to, get the data and you're not cleaning it up, we'll see how to clean up data as we go along. There are various ways to clean up data. So if you get some instances of examples of data that doesn't have the appropriate, what I call features, for example, if you have a system which collects data, for example, and on that system you have cases in which you have people responding, but they don't specify their age, not available. Now you need to decide what to do with that person's entry in the data, in the database that you have collected. Like, which age group do you put them in? They decided to not tell you the age, so that you want to classify according to age, but you don't know what to do with it. So you need to decide what to do with it. And a couple of decisions you can make for a given data point that doesn't have the age value, you can decide to ignore. That's one option. Ignore the data set. So ignore the data point. That's one choice. The other choice you can do is maybe fill it in with some value. Fill with the median value. Whatever the median age for the group of people that you're surveying, find the median and then fill it in. That's the median number. So most likely age out of the sample set that you took. Another one would be that you train two models. So model number one, model number two. This is model number one, you train, and another model. And in one case, you use the feature, use the median with this age feature and age. And the other model ignores age completely. And then use these two models and figure out which model works out better for your data analysis that you may be doing. So there are a couple of ways you can handle. Ignore the data point completely, fill out with some median values, try with both models. Try two different models, one with age filled up like this, or in another one, just completely ignore the age of every data point and just ignore the feature altogether. That's another way to handle such missing data, which you may not have every single attribute for every single data point. You will run into these very, very likely in real life. There are also cases in which there are irrelevant features. For example, if you go to our country here, a list of countries that we were dealing with in earlier examples here. So if you have, let's go see read the names. So we have Brazil, Mexico, Chile, Czech Republic, Norway, Switzerland, Luxembourg. And we somehow include one of the important features, actually not so important, but mistakenly decide to include the name of the country itself as a part of a feature, like name, which actually is irrelevant. So the idea behind irrelevance comes into play right away, is that we are talking about garbage in, garbage out. So if you select and choose that we are including country into, so for example, if you decide that, countries that have W in their name, somehow we make that decision that, we are including uninformative feature sets, for example, the country's name in the body of decision making, the model might pick up patterns that will find that, there is this W in the name of a country. In New Zealand, there is a W. In Norway, there is a W. In Sweden, there is a W. And so Switzerland and a W. And these guys all have more than 7 satisfaction, apparently. So the model, if you decide to include unnecessary features that are not relevant, might pick up some patterns like this, which is, anybody who has a W in their name will have a satisfaction index of more than 7. That is actually not the case, because we know Zimbabwe and Rwanda, they also have W's, and by the fact that we decide to still include the name of the country as an important feature, which actually is not relevant, irrelevant, if we make that mistake, we are actually doing garbage in. So the algorithm might pick up certain weird characteristics, for example, the W pattern, which W means more than 7, but that is not the case. I mean, it doesn't even make sense. But it might pick up such thing if you decide to include irrelevant features from the data itself. So it is important to ignore such characteristics and feature sets from the input perspective of a data. Now, other idea. The other idea here is that you might have a model that may be, fitting all these data points that we have for various countries that we have collected from the IMF database. And we might apply not just a straight line linear model, but a higher order polynomial model, like, maybe a 17th order equation, x to the power 17, or rather a 17 x to the power 17 plus a 16 x to the power 16 plus a 15 x to the power 15, like that. I'm just arbitrarily making up an algorithm that will fit in something like a1 x to the power 1 plus a0, and that is the value of y. If you try to fit such a polynomial, maybe 17th order or maybe even higher order, you might see a particular line that exactly fits every single data point much better. And as a consequence, you might have some higher order, but what the graph doesn't show is something like this. And the graph is not trying to plot that because it is limited by the boundary here. So I'm just drawing it for you. A polynomial might draw its equation something like that. Now imagine if you have a country that fits in right here. Now, maybe somewhere in between 60 and 70,000. So you have the 65,000 as the GDP per capita. Now the value of happiness index for that country will be negative. Ouch. Similarly, here, there is a country with 90,000 GDP per capita, and the value of happiness index for that country will be, ouch, another negative. And so here is a country here, which has, say, happiness number of, say, 78,000, and the happiness of that country people is, oops, what is that? And that is kind of, overfitting the data set that we have. So a higher degree polynomial, for example, 17th order, or I'm just randomly making up, you can actually come up with a polynomial equation that will exactly fit the data. And this is actually also bad fitting, because in real life, you don't see negative satisfaction like these or super high numbers like these for real, because that doesn't even make sense. So fitting something like that is actually overfitting. So another picture that shows us the idea of an overfitting scenario will be on the data that we have in this picture. By the way, this picture is not a part of the book, so I just added it from outside. If you look at the red dots and the blue dots, you will find that, if you put a straight line linear separation, you will find this green line. And then you will notice that these red dots below the green line are wrong. They're showing errors because they are not in the right category of, pink versus blue or red versus blue. Whereas these blue dots here and here and here are also going to generate errors, because what you're seeing is the blue dot should be on the blue side of the line, but that's not the case. So this is underfitting the scenario. The error rates are high. The error rates basically come from this distance, this distance, this distance, this distance, like that. You're calculating these distances and squaring them. And the blue side and on the red side here are also the errors for the red dots that are on the wrong side. And so that's, if you square them, square these lengths and take a square root, that's the error percent you will actually see. And this is your accuracy percent. So that's a linear model trying to fit this data, which actually is underfitting. So this is underfitting. If you look at the other extreme, which is here, and you try to draw a line that very carefully tries to separate the red versus blue, and you get this pattern. It is excruciatingly detailed in terms of making sure that every red dot is on the red side and every blue dot is on the blue side. And that is kind of sort of cool, but we know intuitively that this is bad. This is not how you expect patterns to be. And so the error rate, although is 0 and accuracy is apparently 100, but you put this on a test scenario, on a real life test, and you try to attempt to verify its accuracy, you will also run into errors. The simplicity is to visually inspect whether it looks natural to you. This picture and the line, that way we have drawn here, actually looks very arbitrarily done. And this is what you might end up if you end up a higher degree polynomial, for example, like this picture that I have drawn, like in the equation that I attempted to write. Same thing here. If you try to see a model that might partition things, the red and the blues, in a fashion that makes kind of sort of sense, you will see that there are some outliers here on the red side, or on the blue side, the red dots on the blue side, and on the other side, we don't have any blue dots on the red side. So you have some errors here. So there are some errors that you can measure. And the error rate is non-zero. But you will notice that this might perform better on a future test case that you might put in on a test. For example, you have these new items that they are causing errors. So there is some error. There is this error, tiny little error. And there are some blue dots fitting in here, which don't belong there, but there is also going to be errors that you can measure. And that is leading to this error, but it is much better than extra fitting, or what this is called overfitting, by the way. And you will see another picture example. And so a good model that looks like this, for example, for this data set, is going to predict more accurately on any future data that we don't know the label for. So that is a picture of what I find is a good joke about what is the best way to explain overfitting. Is when you design a bed, you create the bed platform exactly to fit what the person is going to be sleeping like. And then the moment the person takes a turn, we have a problem. And that's just a, it's more of a, what I call meme. So yeah, this is bad, overfitting. So now what we need to do is understand the idea of dealing with data in terms of making sure that it generalizes better to any future data sets, for example. And so here, if you look at the blue and the red, the country data that we had to begin with in our first example that we ran the last time, if you use just a linear model, what you will end up with is the dashed red line here. That's just a linear model, this one. If you use a linear model on partial data, you will get the dotted line, which is kind of going on the up direction, because we are using only the blue dots and not the red dots. Now, if you take regularized linear model on partial data, what you actually will see is this solid line, which is kind of sort of a middle ground in between the data points. But again, the data set here is small, and the model here is a linear model, which is something to keep in mind, that it may not actually be representative. Now, having discussed this, the idea that we want to go is to understand how do you use the concept of the slope of this line versus the slope of this line versus the slope of this line. The slopes change. And what is the right slope? There is no right answer for this unless we test it for a future data for which we don't have a label. And that's the true measurement of success of any given algorithmic choice, given your data point that you may have at a given, in a given example. Having said, I think we should understand what would be the case of a end-to-end example, which is, I think, coming up pretty soon. So if I want to make sure that I think these are things to just recap. So I'll skip ahead. And what I want to do now is to help us understand that we have, say, for example, set of data points. Say, I'll grab a sheet of paper here for us. So I will open up this in a new window and adjust that. Here we go. So the thing that I was talking about is that if you have, give me a second. If you have a number of data points, let's call them, for simplicity, we have 100 data points. Now, what we want to be able to do is come up with a model, and the model that attempts to use the data available to us to create predictions for a future data point, like the new data that comes in. And we want to be able to estimate or make a projection for what the outcome will be based on the data that we have input into the model. Now, the challenge that we run into is that we have these 100 data points. We want to create a model using that. And we want to test whether this model is actually predicting accurately or not. Accuracy of the model is hard to measure unless you have new data. And this is going to be in future, so we don't have it right now. The future data will arrive at some point. And we don't have that data right now because it is in future. So what we need to do is to be able to test this model that we are going to come up with. The challenge that we typically have is the number of data points we have is limited. Now, it doesn't have to be limited to 100, but it is limited. It is not infinite, not infinite. It is some number, some large number, but it is that number. So the way to make sure that we can accurately test our predictions from this model is to not use the entirety of data to begin with. And that is something that you need to understand and remember, is that even if you have a ton of data, say for example, 100 data points, and you end up using all of these 100 data points to create a model, now you have nothing to test with. And that is a challenge. So how do you overcome that challenge? Is that you basically don't use all of these data points. Instead, what you do is you have so many data points, let's say 100. And so you take a portion of that data set, let's say 80 and 20, and you divide that into the data for your fitting a model, and then you come up with a model that will be able to make a prediction. And then this becomes your test set. And so the data point that you will actually use to create a model and to start to make predictions will be using only a portion of your data set. And you will not touch this until you are ready to go production with your data set and with your prediction model. And at that time, you will test with this and you feel comfortable about it. And then future arrives, future with new data points. And then you hope that this is what will be the real life test. So when you deploy it in production at that time, then future arrives and new data comes, and then you are able to make a prediction, but you are not looking at this data at the time when you are actually building a model and attempt to make a prediction. So that's how you typically divide in a given project. So the idea underneath is that you are basically partitioning your data set into 80% data for training and 20% you hold out for testing in real life. That's how is generally considered a good practice, that you hold out certain data set and not use the entirety of your data set, all of it, in fitting a model, because then you have no way to actually test for accuracy of how well did you actually use your machine learning techniques to make a prediction for a given set of data that you might have, say 100. So that's why you reserve this set for test. That's the underlying idea. Now, I think this just finished. So you should go and, the exercises here are for you to, basically they're simple questions to answer. You should answer it yourself. If you are unable to answer, you should always come back to me on chat and talk to me one-on-one if you need to. But these are something that I think you should go through on your own, which when you study these things. Now we have some more write-up here, which is not a part of the book. This is from another article from McKinsey. So what I'll do is I'll extract this for you. This is more of an intro article that I have just embedded in the book. And I think it's a good idea to just grab it. So I'll remember to pass it on to you guys on your messages in Slack chat. And I will extract that information and send it to you, which is a good read for us to understand what types of algorithms. And this is like a CEO level understanding of what machine learning algorithms are available and what are the sample business use cases. So that's the idea here. So linear regression, typically used in this business scenario, logistic regression used in this business scenario. So you can read this on your own. I'll send this out to you later on. So it is probably about 8 pages or so, roughly 7 pages or 8 pages. It's an executive guide to AI. That's the idea. And there's some history here as to what is going on. And from the top level to remember why artificial intelligence now. The key thing to remember from a really top level are there are 3 things happening. One of them is that we have, cloud with us. Cloud meaning there are lots of cloud resources. We have all the big companies, Amazon, Google, Microsoft, there are a bunch of other players. that some of you, I think, already know this, but the cloud is available and it is cheap. I mean, cheap, I should say. Yeah, really cheap, very, very affordable. You can get a multi-GPU cluster to run your TensorFlow operations for a few bucks an hour, as opposed to spending like $100,000 on a large, gigantic machine with multiple GPUs. You don't need to do that these days. It is cheap. So there's one of the driving forces right there. Affordability of machines available to you in the cloud. That's one big thing as to why artificial intelligence is growing in its adoption in the business. The second thing that is important to think about is we have advances in math. You know, lots and lots of smart people have already developed and refined algorithms, and that work is still going on even right now. And that has, basically led to the creation of these libraries that we talk about, like scikit-learn, TensorFlow, and there are many such, by the way, libraries. These are just two open source libraries. Let's go see some libraries for us. Open source machine learning libraries. And there are quite a bit of them. Here are top 8. Yeah, you can actually see comparisons. And so here is TensorFlow, Keras, scikit-learn, Microsoft, Theano. Microsoft, I don't know if it is open or not. It says open source framework, so fine, that's open. Theano is open, Cafe, Torch, Accord.net. It is also open source. So the underlying idea is all these tools are available to you, and we are using just two of them, the scikit-learn tool and the TensorFlow tool. So that's the math implemented, ready for us to consume. Cloud is there for us to consume. And in addition to these two things, there is one more thing that is happening, which is data, explosion of data. And we have Internet of Things, generating data, generating sensor data points. People in various companies are actually collecting, storing this data for many, many years now. So they have records and records of data that now need to be appropriately understood, labeled, cleaned up, normalized, and then used in a model fitting in a structure that we'll be doing that soon, by the way. And so these three things: cloud as available to you. All of us have it access, very easy access, very cheap and affordable. Most of our companies have tons and tons of data points, and math has amazingly improved and implemented. So the combination of these three things is what is leading to artificial intelligence growth across the industry. And you will see the latest developments as late as, we have AlphaZero beating the game of Go, beating this guy who is the world champion. So Google's DeepMind project recently beat that by playing the game of Go with itself and learned. And hardware advances like TPUs, tensor processing units that I think I showed you a small picture of. Those things are available as recently as last year. And still further work is going on, which is going to further basically improve use of machine learning and artificial intelligence as applies to business. Now, having discussed this, here is the second chapter, starting with an end-to-end exercise. And that exercise actually is hands-on. And it assumes that you have, basically gone over the prerequisites, which are Python, scientific Python, math, and there are three scientific Python tutorials: NumPy, Matplotlib, and Pandas. So I'm assuming that you have had time to review these at least. They're not so complex, not so big, but if you want me to review these right now with you, I'm okay with doing that. If you want me to review this on a separate session, I'm also okay to do that. So just ping me on Slack. We'll do a one-on-one session, just making us, walk through this NumPy, this Matplotlib and Pandas. But right now I am planning to skip these things because I am assuming that you have already done it on your own. Like the other day we discussed the linear algebra tutorial. I'm expecting you to go through this on your own. If you want me to cover this right now, tell me. I'll do it right now. If you want me to cover this later on a one-on-one session, please tell me. I will do that with you one-on-one.
I'll cover it on my own.
Having said, let's go jump to the section on second chapter, which is what we want to cover today. And that is what is loading up. That is matching this second chapter book in the book, which I think you already have. And here our goal is to work as a person who's helping a real estate company. So the real estate company will be something like, your Zillow.com or Trulia.com or all those, basically, these guys. You probably know them. Trulia, the other one. Those are the kind of companies that are, helping people buy and sell homes on the internet. So here is a home listing. You may have seen such a thing already, Valerie. So I'm not making sure that you understand what I'm talking about. That's what is an example of a real estate company. Now, the way that real estate company does, it makes money by making investments in appropriate real estate properties. And to make an investment, one of the inputs that is necessary is to assess the value of a home. Like, if you have a home somewhere, this home, you need to make an investment. So you need to find out how much is the intrinsic value of the home. Is it 100,000? How many? Yeah, 100,000 or more, or 200,000, or maybe 500, depending on what you think is the market valuation. And that's the idea behind assessing value. If you're able to assess the value correctly, then you can then decide whether to invest in such a home. If it is valued at 200K, you want to maybe make an investment in that home for something like less than 100K, so that you end up making intrinsic profit. And over time, when the valuation grows up, you might want to sell and actually cash out, and that might make you money. So the idea that you have this number at hand when you are able to assess the value of a given home for a given particular, in a given location, you can better decide whether to invest in that home or that collection of homes or that set of property or not, based on insights that you can make a correct estimate. If you make an incorrect estimate of the value of the home, then your investment efforts in that particular property may go bad and you might end up losing money. So this is a critical role that you are getting hired as a data scientist in a company that is going to focus on real estate investments. So that's the big picture. So we understand the big picture now. Now we need to get the data. So we need to have data to help us come up with value of a home. The data we need is something like value of homes in the area, whatever that area is. So in this example, I think it's the state of California, and there are several data points available, which gives you value of homes in a large number. So that quantity of data is already available. We need to discover the data, visualize the data that we do to have to understand what are we looking at. Then we come up with a model that we want to maybe fit into that data that we have. We want to train our model. We want to fine tune our model. And we want to talk about our solution to make a educated guess of a value of a home where the company might want to make an investment, and then run this as a system, as an automated system that looks at new data points as it comes up for a request for a assessment of a value of a home, and then give an output. So that's the idea behind launching your project, to come up with a correct value assessment of a given home and maintain your system. So that's the concept. Now we're dealing with real data. Now there are several repositories where you can actually get real world data for a variety of data stores. So here are some links to places which are well-known open data repositories. You can just get data from a variety of places. Sometimes, in large businesses, you already have the data in your company. So you just use the data. You don't even need to go outside to look for data, because you typically work in large companies which have been collecting data for years and years. The time is now to take a look at that data and actually make use out of it in an automated fashion. That's the ultimate goal of using these techniques and applying that to the data you have in your companies. So what these examples actually provide is ready-made data sets available publicly, like open data repositories, for example. And that's in this particular example, in this end-to-end machine learning project, what we are really going to look at is this data set here. It's called the California Housing Data Set, Housing Prices Data Set. It is from the StatLib repository. So there is this link here that you can go and visit. It is figure 2.1. The data is actually old, so old data. It is from a time when actually homes in California were kind of affordable. Not these days anymore, really, really expensive these days. Like even in our area and where we live in Seattle, the homes are expensive. A mainstream home is like $1 million these days. A mainstream as in 4-bedroom home. So on the area where we live in, almost every home is $1 million. And same homes in the Bay Area and California area, and especially this spot in the map that you look at is Silicon Valley. This spot in the map that you're looking at is the Los Angeles area. So both these are hotspots, as you can see from a graphical representation perspective. So the data that we are going to look at is already plotted from a picture, from a graph perspective. That's the California housing prices data set as shown in this figure. So what you're now looking at is the cheapest home you can buy and the most expensive you can buy in 1990, by the way, old data. And that data is described in this picture. So if you see red colored items, like red hot items, like right here, that's what you see these pockets in this segment, and some red items here in this segment. So that's what the red ones are. So expensive homes and other homes, like yellow items in some pockets here, some pockets here outside, outskirts, outside the main areas of Silicon Valley in San Francisco and Los Angeles. That's what you see, the cheaper, or rather median homes, and some cheap homes down here, which are blue and light blue in color. They are kind of spread out all over the state of California if you look at this picture. And that's the data that we see visually. Now, what we have in this example is that we have understood what does it mean from the data that we have. So we'll actually look at the data set itself and try to understand how do we divide the data in terms of what is known as a block group or district. Or a block group is typically which has a population of 600 to 3,000 people. So we are dividing the region, the map that we have, in smaller block groups. So we can use that block group as a way to predict the price of a home in that block. That's the underlying concept. Now, in this, there have a beautiful tip, by the way, in the book, and I think this is something you should absolutely read. And that tip that they are providing is a project checklist. And this is in the appendix B in the book. You will find that this is actually a beautiful list of things that you can keep track of. So we should read that later on, not right now. But this is something that when you're starting to work on a new project, you should read that. Let's go take a quick look at what it actually does. So I'm going to just open this appendix B. Was that appendix B? So we'll just go straight to the appendix if we can. See if we can find it, appendix B. And that's the checklist that I was talking about. So checklist, explore the data, get the data, frame the problem. There it is. So that the checklist is basically from a top level perspective: frame the problem, look at the big picture, get the data, explore the data, prepare data to expose the underlying data patterns, explore many different models. Like that's the key thing to remember. You want to try like a bunch of models, 3 to 4 different types of models, and fit each of these models and see which one works best for your example. And you make a short list of maybe 1 or 2 models that works best. And then further tune what you're dealing with. And tuning I'll walk you through what a tuning of a model actually means. And then, put them together to create a solution that will be presented to your management team. And then you launch the campaign that you have, or launch the particular model that you have put into play, put that in production and see how it actually works out for you and maintain it. Maybe improve upon it. And that's the overall checklist. And we'll go back to what we were doing on that, because that checklist, I think, is kind of important for at least me to point out to you. Is something that I like it in terms of what it helps me in as I work on a new project. That is something that I find it actually useful. So let's go follow that same checklist. Exactly, that's what we are going to go through in this project. And we will begin framing the problem. Like, what is the big picture situation? What exactly are we trying to do? So you ask your boss the question, hey, what are we trying to do? Why are we doing this? Why is it important? And what exactly will the output of this machine learning project, where will it be consumed? So maybe if you create your district level pricing assessment, so you have the data that comes to you from some source, you have the district level data that you collect and then you use in your system, and you produce an output. That output may be going into some other system in your company, and then along with that output that you produce goes into a district level pricing system. And then there are other signals that other people may be generating, and then these signals from other places and your estimation of a price in a given district maybe become an input to the actual decision making of where should the company be investing. And that analysis decision is actually what ends up in where should we invest, that decision point. And that's essentially what translates into money. So from a usage perspective, the idea is that you need to know exactly how your output is going to be used. And if you're not clear about that, it becomes confusing to you as to what exactly should be the goal. For example, you need to be clear about what you are going to produce as an output. Is it a number? Is it just high, medium, low? Or is it something else that you expect these guys to be consuming, because they are going to use your output as their input? So you need to basically understand what exactly they expect you to produce. Maybe it is a ballpark number that you need to have. Is it 100K, 200K, or 300K? Is it small, medium, large? Or is it a number of 314,5365 dollars? Is it that precise a number you want? What kind of output is expected? I think that is the top level question. And then you go deeper in terms of understanding what exactly is the output expected. Are you feeding that output to another system in the overall company's operations? And how exactly are the outcome from your project going to be used in another decision making? Is that critical, and how does it affect your company's revenue? And that is something needs to be understood. So what we are really looking at is a pipeline of data, as the data flows through a pipe all the way towards a decision. So that's the underlying concept of a data pipeline, where you have data flowing from various sources into systems that will come up with a prediction, an estimation, or a guess, an educated guess of something that depends on input data that you have accumulated over time. You applied machine learning models to make a prediction of future data that will be expected, that you want a estimation for. And that's the idea behind a data pipeline. Now, at the top level, you need to remember that this pipeline is asynchronous, async. That means each of these things is not actually like water flowing from one end and coming out of the other. That's not the idea. You might have data coming and it gets processed and it just stays there. It may not be directly readily used, but it is used whenever it is needed. So it is by structure asynchronous. Each of these components within the pipeline that you will see is basically self-contained in that it operates by itself. It knows what to receive, and it knows what to produce, and it produces that and just puts that in the output and does its job. They're basically fairly independent of each other, but structured in a pipeline sequence so that they can be actually used to make a prediction of the entire end-to-end pipe that you have. Next question to discuss here is to understand how will you're going to use the data that we will be creating. Imagine if a situation when you don't have a system that actually produces what you are going to produce. What is it that what was it happening without you? So if you have this project P that you want to do, imagine if there was no project, what was going on before the project? And that is something that you should actually understand so that you know better exactly what are you replacing. So the other older methods of doing, say, for example, the boss answers that, we were going to ask our experts who are in the area, ask them manually, hey, come up with an estimate, and the people will go gather information manually and come up with a median number for us to consume. So that was the older system. Now what you need to do is to replace that manual estimation yourself by creating a machine learning system that is automated by itself and uses data to come up with the work that was earlier done by people. And that is something that you want to understand very clearly. So having people do that was expensive. Now you will have a system doing that, and that will reduce the cost of the overall operation. So that's how you should think about adding value to what you are going to do for the project that you have in hand, and that you will understand what are you really replacing from creating a new structure in your data pipeline. Now, before you begin, you need to understand what type of problem this is. Is it a supervisory learning problem? Is it unsupervised problem? Is it reinforcement learning? Or is it something else like a classification task or a regression task, or a class in which you are estimating probabilities of something happening versus that? And that is something that you need to be very clear about. Also, you need to be super clear about is it going to be a batch process or a online process? Meaning, are you okay if you take the system entirely down for a night and come up with the system again next day morning? Is that acceptable? Maybe that's the case in case of a real estate investment, but we don't know. So that is something that we should actually very clearly ask for, whether a system that you're dealing with is batch learning, or is it expected to be continuously operating online? And once you have those answers, then you proceed forward. And let's see, in a typical scenario, you find out that it's a typical supervised learning task, because you are provided with labeled examples. And so what we are going to now do is to, when we have labeled examples, the idea is to come up with a real number output. Real number, meaning the value of the home or value of the homes in a district or any of that is basically a number, a real number. And when it's a real number, the algorithm that we will be using, or the task that we will be actually running, is a regression task. If you recall, regression is basically something to deal with a real number, as opposed to a classification task would be something that you classify that into small, medium, and large prices, or maybe a yes or no discussion or something of that nature. So it's clear after your discussion that this problem is actually a regression problem and not just a classification of pricing, small, medium, large, or any of that bucket. So you're basically classifying something in these three buckets, for example, is not what you're dealing with, but you have to come up with an exact number, an estimate of value of a home in a district. And that is where you want to come up with a prediction of a value. So it is going to be a regression. It is also a multivariate regression, meaning there are multiple inputs that you will have, for example. And I'll exactly describe what that multivariate regression is going to be. For example, in our earlier example that we discussed, this GDP and life satisfaction index, it was basically a single parameter that was being handled. We know what the GDP is. So we had like GDP here, and based on that, we were able to predict life satisfaction index. And we had some data points all over the map, and we just drew a line and we said, okay, for this GDP, that's the value of LSI. So that was easy. We had just one variable, so it's univariate linear regression. Whereas now we will have multivariate. So multiple variables like GDP was only one. In our next examples, which is this one for the housing prices, we'll come up with a scenario which will actually deal with multivariate regression. So that's what you are going to deal with. What does that really translates to is that we will have multiple variables to deal with. For example, let's go see an example. In the case of housing, you could have measures that relate to, let's go see the picture so we can talk about that better. So here, if you look at distance from the ocean for this home, how much is the distance from the ocean versus for this home, how much is the distance from the ocean? Maybe that impacts the price of homes in that area. If you have, say, this region or this area, which is kind of, a low price area because it is far away from these centers, both these centers. And you will have other parameters that will actually dictate value of a home in that region. And those may mean, a home, if it has like 4 bedrooms or maybe only 3, that will also dictate whether that price of that home is high or low. Other factors like, how many rooms does it have? Is it, these are the bedroom counts. How many total room counts? Does it matter how many rooms a home has? Maybe there's a home which has like 13 rooms. Does it make the price go up or down? And if it is 12 rooms, is it going to be expensive or not? And how much, by how much? Those are the characteristics that we are looking at, that we need to be able to keep track of and account for when we are dealing with data. And it is not just a univariate problem in that we have multiple things to think about. And so number of bedrooms, number of total rooms, total number of rooms, distance from ocean, like that. Those are the characteristics which are generally collectively called features, as we will see, will be the multiple variables that we will be dealing with in order for us to come up with a number for the regression at hand, which is what we are going to deal with. That regression value will come up with a real number to predict the price of a home. And so we need to now estimate what is going to be, in these guys' language, the performance measure. And actually, when they say performance, they mean accuracy. It is a measure of accuracy, as how accurately are you actually coming up with the value of the number that you are trying to guess, which is the regression situation. You're going to come up with a number, not just saying small, medium, large, not just a classification problem, but actually a value. So now, if you have a value, and the value that you expect to have could be here, and so the difference is the error. That's how you should think about these errors. So that's what they are going to now measure the error using a root mean square error function, RMSE. And what I just draw on the earlier picture, what you're looking at in this mathematical equation essentially is a simple calculation of root mean square. Root mean square basically means you take a square of square minus, so the function hx basically stands for the valuation that you estimate, and the actual value it is going to be, and you would take the difference, which is the distance between, or rather the calculation or the graphical representation of the error. So if this is the h of x and that is y, the difference in the two is the error, which is what you see here. Now you square it for all the data points, and then you take a root and you divide it by the number of data points. That's what you have here. From 1 through m, the m data points, you take hx minus y and square it and take a root at the top. So it's root mean square error. And that is one metric. There are various ways to calculate error or loss or these functions. And that's what we want to really, really minimize. We want to minimize the error so that the predicted value is actually matching what we had in mind to begin with. Because if you actually minimize the error, you have a situation in which h of x and y are the same point. No error. And no error is kind of a strange case. So very, very small error is what we really expect. So we have h of x and y almost there. And so the distance between the two is very small. And we are looking at it at multiple data points across in the entire data set. That's what we are really measuring. So the entirety of data set, m data points, that's what you see here. M is the number of instances in the data set that you are measuring RMSE on. Now a little digression on this measurement of error. This is what we want to really minimize. And so the idea of minimization of an error, we are looking at a mathematical function which has a root and a square. There are other ways to actually come up with a estimation of a function that attempts to calculate an error. And I will just draw it, or write it down for us simply something like this, taking an absolute value. In other words, we are calculating abs of hx minus y. So basically calculating the absolute value of these things. That's another way to, and then we have to sum these up from I equals 0 to m, or rather 1 to m. And so that's another measure of calculation of the error function. Like here, hx minus y is the distance between the 2 points that I had drawn, maybe here and here. So one of them is hx and the other one is y. The distance between the two is the distance that I want to measure. And so I can measure it in another function like that, absolute value of x and hx and y. So we are making the absolute value by putting these vertical lines here to basically decide to calculate the distance, as opposed to ignoring the fact that what if hx is higher than y, or y is higher than hx. So basically you're ignoring the sign of this plus or minus, whatever that is, by taking an absolute on that. And that's another way of calculating an estimation of the deviation of estimates from the real values. So that is called an absolute measurement of error, as opposed to root mean square error. And these are just two. There are more methods of measuring these error functions, as we'll come up and we'll run into them later on. The idea essentially boils down to what I just draw simply h of x and y. The distance in the two we want to minimize on the entirety of data set. So from 1 to all the way through m, all the data points, that's what we want to aggregately, at an aggregate level, our algorithm should come up with the valuations such that the value is as close as to y as possible for the entirety of data set and minimize the error. That's the underlying concept behind any of these algorithms that we'll see that. What you will see is various ways and methods of measuring error, various ways and methods of approaching to the possible lowest possible error. And I'll maybe finish off the digression with a picture that you will probably have easy to understand. The picture will go something like this. Rather, I should maybe not draw a picture, but see if I can find a picture for you. Convex function graph. Let's see what a convex function is. So here is the Wolfram convex function Wikipedia. That's a good picture right there. So we have a simple convex function that looks like this. What we're really trying to do in this picture is to look at and understand what is the lowest value of the black line. And when I say black line, I actually mean this line. Oops. Hello. Hold on, something's going wrong. I'll clear it and go back to that one again. And I'm talking about this line, the black colored line. And I want to minimize, or rather find out the lowest point, which happens to be right there. Oops. What is going on? I think that my full screen is erroring out. So let me just change my browser. Change my browser to Safari. And here I will go to convex function. So I'm clearing it and starting to look at a convex function. I hope you already know this idea of convex versus concave functions, convex functions. And if you don't know, just quickly look at what this example attempts to show you. And so here is a convex function, and we are looking at this illustration in which we are really trying to find out this point, the lowest possible point of this function. So that shape of this function is convex, in that there is only one such point, which is the minimum or the lowest value for that function. That's the underlying idea. There's only one minima. The word is minima. So what is minima? Let's go clear this again and look at the other pictures that we might have in a three-dimensional view. So here is a 3D picture of a convex bivariate convex function. So here is the equation for that. And if you take grapher and try to plot a 3D default, choose, and see if we can plot a function like that. That didn't actually plot what I expected, but you can possibly tell that this picture attempts to illustrate the low point right there. If you look at this lowest point on this axis, actually it's not a good representation of what I wanted, so I'll ignore this picture. But you look at no, it doesn't represent what I want. So let's go back to don't save and close. Now what you see in this picture is definitely the idea, which is what I wanted to talk about, is to find the lowest possible point right there on the cup or the convex representation of this little bowl, if you will. And that bowl has this point, possibly the lowest bottom point. Now, in other cases where the function is not convex, what happens is that you will see situations where a function is not convex. And I'll see if I can find a picture of non-convex functions, non-convex function. And non-convex functions are something that do not typically have. There, that's a good picture. So if you look at this picture, you have multiple lowest points. Actually, if you flip this picture upside down, maybe this is a better picture. So these are multiple lowest points are clearly visible in the picture here. There is one low point here and one low point here. Now, the way these algorithms, almost all of them, the way these algorithms will attempt to find this point or the lowest possible point is simply mechanical in nature. And I'll walk you through that mechanics of it in a visual form so that you will understand what's going on under the hood. Mechanically, what happens, if I may clear this and make it clear and make it go away and expand on this picture. There. And so the picture is there for us, so we can use it. Now here in this picture, if you look at mechanically how these algorithms actually travel, and literally they walk, they actually travel to find the points of minimum error. This is what they want to find. And so say, for example, this is your error function. And if it happens to be convex, that is beautiful. I mean, beautiful, I'll tell you why. So you have this error function, you somehow think about it as something that is plotted out for you, and you visually inspect the error function, and you want to get to this point. So you begin at a random point, literally anywhere, random, and just say, I land here. So that's the point I land on. And so I am here, and I want to find out which way is the minimum. So what I will actually do is attempt to calculate the slope where I stand right now. So if I am here and I calculate the slope of that function at that point, and you will find that the slope of that function is y over x, which is positive. And so what you will typically do is you are at this point. So say you're at this x1 value, and you want to go to the next value. You will want to find out mathematically, should you go this direction or should you go that direction? That's what you want to find out. And so the way you get to the next point, say x2, will be basically calculated based on x1 minus some alpha, which is the rate of learning, and the slope that you have. So what you're looking at is the slope here that you calculate is the slope of the error function at the point where you are currently standing on, and then you come up with the value of x2. So the x1 right now is here, and you want to go somewhere else, either left or right, but you don't know which direction you travel. And that estimation of the next step that you want to actually walk towards, which will eventually take you to the minima here, that's what you want to get to, because that is the right answer to minimize the error. That's what you really want to do, is to minimize the errors on an aggregate basis. So you come up with a math function, and then you calculate at x1, where do you want to go next? And you come up with this math. So this is a constant. It is also known as learning rate. And what you will do is estimate the slope where you stand. So you're standing right there. And so you estimate the slope, and the slope happens to be some positive number. I'm estimating to be roughly about 1, just visually saying, because this length is equal to that length, just estimating that to be 1. So you get a y over x, or delta y delta x. So the slope is 1 estimated. And then what you have is you need to come up with this calculation, because this is 1. And so you can ignore that. So x1 minus some number, and that is typically a constant in one pass. So in one pass, you can come up with some learning rate, the rate at which you are learning to find the minima for the convex function to minimize the error that you have. So you will travel towards that direction because of the reduction by the learning rate. So you will move yourself to this direction in an x2 position, which is exactly alpha in that direction away from x1. So you x1 minus alpha is where you end up, and then you reach this point, and that is your x2. And there you calculate the slope again. So you have x3 now, and x3 equals x2 minus alpha slope. And slope is the calculate that you will calculate at that point, which means you will again take the slope like this, y over x. And it will be, I'll estimate it to be again roughly about, say, 0.9. I'm just making these numbers up, but it is positive, definitely. And so you come up with an alpha, 0.9 alpha. So this time you will move from this x2 to that direction, say x3 is right here, and like that. So you're slowly traversing towards, as you will see, the slopes here are also positive, and you end up here next time, and next time here, and eventually you will reach this point, which is going to be your x whatever number, and then you will have the slope is almost 0. At that time it is almost flat. So these numbers are close to 0. So that is also close to 0. And so very small negative number. So you're reducing this x2 or the x previous by a very small tiny number, and slowly and very, very slowly you are approaching that position, which is what you want to find out, is the right point at which your error function is at the minimum possible value. Now, if you adjust your learning rate or the alpha value to be a little bit bigger than what you had, so now you have x1, which is the beginning point, and you come up with an x2, which is equal to x1 minus a big alpha times slope. Now what happens here is that your alpha is big, so your slope is estimated to be 1 to begin with. So you end up something like alpha being 1. So you just reduce x1 minus a big alpha, multiply by the slope, and you end up, boom, here. And then this is your x2. So now you find out the slope at that point, and the slope happens to be negative, because that's how the structure is. So y minus y over x. So it's like a really big number, actually. It's a very, very steep slope, negative. So you get x3 equals x2 minus a very big alpha multiplied by a big negative slope. So you got a really big negative slope, which means, say, for example, it is like 3 negative. Now you're dealing with a weird situation. What you're running into now is an x2 plus 3 and a big number alpha. What does that mean? You're traversing x3 equals x2 plus 3 alpha. That means you are going all the way 1, 2, 3, somewhere here, and that's your x3 value. I'm out of bounds now, but I just jumped. And if I extrapolate this curve, it's going to be like way all the way up. And so we end up in that some weird location here somewhere. So we are digressing, and instead of converging to the minima that we want, we just ended up from here to there, and it's like going all over the map, and it's not going to converge. So the critical thing to remember is that this alpha choice is also known as the rate at which you learn to find out the minima, is one critical input that you need to keep track of and adjust as we go along, because that dictates how much will you move in this direction and this direction and this direction. Or maybe if you have a bigger alpha, then you go move this direction, and then you move this direction, and then maybe you move this direction slowly. That might happen. So depending on how much alpha that you choose, you might end up at the minima. Or if you're exceedingly large learning rate, you might end up outside of the curve in some random location, and your algorithm will never actually converge. So that is the situation with your learning rates. Having discussed this idea, let us now look at the other picture, which is a non-convex picture. Now here, the same concepts apply. You really want to get to this point, but if your beginning point happens to be a random number that takes you here, now you calculate your slope. That comes out to be roughly about 1. And you have a learning rate that takes you here, because that's what it will take you to. It's a positive slope. The learning x2 will become x1 minus some learning rate multiplied by slope. And this learning rate is assuming that it's a reasonably small number. So it will take you that direction, and here is your x2. And then it will take you further that direction, because it's still a positive slope. So you will reach and ultimately here, and slowly you will reach the bottommost point. But again, this is not the right answer, because it is actually higher than this number. So the error is bigger than this. So you really want to have the lowest possible error from the function's mathematical perspective. And you cannot get to that in a systematic, programmatic way, because the underlying error function is not convex. So that is the reason why people have come up with a variety of methods of measuring errors. And through research, what people have done is that they have come up with methods that will lead to convex error functions. So you will see that a simple error function can be as simple as, distance between the two, or maybe sum of squares and a root of that, like that, summation and root of that. That's a root means square error function, or simply taking the absolute value of the function. So there are simple methods, but there are other ways of calculating errors that may look unintuitive to you, and we'll see some examples as we come along. And those error functions are typically chosen like that because the end product of the end result or outcome of the graph that looks like a convex function from an error calculation perspective, and that makes it easy for the algorithms to converge to the lowest possible point. That's the reason why people have come up with a variety of different ways of measuring error, which doesn't have a square function or an absolute value, but something that will lead to a nice convex error function. We'll see some more examples, and you will understand what I'm talking about, which is basically I'll compare these things with a simple convex function versus something that may have multiple minima. And so the real minima is actually this one, but you might get stuck with a non-optimal minima, the local minima, as opposed to the global minima. So you want to get to the global minimum error value. You can get that if your function itself is convex to begin with, but if your function is not convex, you will have hard time converging to a global minima, because it will get stuck here. It will get stuck here or here, wherever you land. So it is difficult for you to actually reach the lowest possible point. The algorithm will not actually reach there. And that is going to be a challenge. And that challenge has been solved by structuring your error calculations in a different mathematical formulation that leads to convex functions. That's the concept. In this example, we are still using RMSE, which is okay, and it's not going to cause us trouble. This is just a beginning example. Now, what we are looking at is here, M is the number of instances that we have. If you are evaluating the RMSE on a validation set of 2000 districts, then M is 2000. So the idea behind xi is the vector of all the feature values. And these are the feature values as we'll describe. For example, the first district in the data set is at a latitude, longitude. So we have these latitude, longitudes basically represent where exactly they are on the map. How many inhabitants, what's the median income of the people that live in that region, what's the median house value. And we are ignoring some of the other features for now, but that's how you will represent the xi function. Now here is an example of various features listed out. And this is 118, which corresponds to the longitude. Then we have 3391, which is longitude. This is your latitude function or feature, latitude feature. We have how many inhabitants. And then we have a median income in that geography, in that block of houses. So what's the median income? These parameters actually are going to be used as input. And what we are looking at is a matrix, or rather a vector of all the feature values for the first instance. That was the first district in the data set. So we have data for multiple districts. We're just looking at the first one. And these are the important features that we are taking into account in this example. And the y value corresponding to that happens to be this. And that is a label that we already have for our data set. That's the idea. We already know the valuation. That's the valuation. And X is a matrix of numbers of all the features that we have. And what you see, this X versus this X, this is a small x, if you will, and this is a capital X. And what this X does is it is the collection of all the X values, the lowercase x's. So we have X1 transpose, X2 transpose, X3 transpose, and X2000 transpose. And so we're creating a large vector of vectors. And that is what we have structured it like this. Now, in our example that we are looking at, this H function is what corresponds to your system's prediction function or hypothesis, is when you are making an estimation of what that predicted value or y hat value is going to be. And then you calculate that y hat to be this number, as opposed to the actual label is that number. So the distance between the two is 158K minus 156K, and the difference was 2000. That's how you will calculate the error function. So this is the prediction error for the first data point. This is what you come up with in your math. This is the actual label. And this is what your math shows. Your algorithm will predict that number, and the error will be 2000. That's the concept of calculating these errors. And so you will further see that we have slightly ignored the root part of the RMSE. So RMS error. What we are now looking at is the mean absolute error. So the other way of calculating error functions that I described early on, which is We are not doing the RMSE, but this representation, which basically is the edge of x minus y, and you sum them all, and then you take an average. So both these methods of measurement of errors are measuring the distance between the two vectors, the distance between the vector that you come up with, for example, doing your math, and whatever the label actually is from the input data's perspective. And the distance between the two are two different ways of calculating. One of them is RMSE, and the other one is MAE, or mean absolute error. Now, if you will find it is up to actually you to calculate which one is going to be a better choice. There actually, from a usage perspective, as long as you are able to get the error the lowest, that is going to be low for this as well as low for that. It doesn't really matter. The goal is to actually minimize the error itself. Now, a measure of that error can be root mean square error or mean absolute error. That really doesn't matter which one is a better. So there is no such thing as a better versus worse way of measuring your error function. The thing that actually matters is whether we are converging to a minimum from an error perspective or not. If our algorithm is not converging properly to the lowest possible data point, then we have a problem to deal with. And then we have to maybe rethink as to how we are actually calculating the error function so that it actually gets us a nice little convex shape from a math perspective. So our algorithm can travel, literally walk along the path of lowest gradient, the slope, and get to the minimum as quickly as possible. That's the idea behind, which I just described, was the concept of gradient descent. Sorry, I should write that on clear drawings. So I should write here, what I described was gradient, which is slope, and descent is like going down. So you're going down the hill on a convex shape. That's what you want to go quickly to the lowest possible point. And that's the idea behind gradient descent. You are traversing down the slope to get to this point as quickly as you can. Or from here also, is also downwards. From both directions, you essentially reach this point. That's what you want to get to, gradient descent. Maybe my accent is not the right way to say the word descent, because there is another word called descent. So I hope you understand what I'm talking about. This descent. Now, this descent. That's what I'm talking about. An action of moving downwards, dropping or falling. How do you say that? Yeah, I'll figure out later how to pronounce it correctly, if I not confuse anybody. So right there, that's the pronunciation. Did it say anything? Maybe it didn't. Whatever. So let's now check our assumptions on the data set that we have. Now, the assumptions that we need to go and cross-check are that we would like our system to not just convert into categories of cheap home, medium-priced home, or expensive homes, but actually come up with a number. And if it is this classification style, then maybe we need to think about our algorithm choices to begin with, and or outcome or output choice to begin with, as opposed to spending a whole lot of time coming up with an exact precise number, which is going to be a regression task, which is what is going to be the case. But you're going to know these things up front and check with everybody in the team that, hey, we are actually going to calculate a number for you, as opposed to just giving you small, medium, large, cheap, medium, expensive kind of classification and not a number. So that has to be, assumptions have to be clarified before you code. So now that you have your data, let's actually get the data. So now we will open our notebook right there, go to chapter number 2, which is this one, and get the data. We can get that data from the, I think in your repository. If you, I know you have cloned it already, so you have pulled. Actually, you can ignore this. So you have already done this. So you have the thing functional in your notebooks right there. You just open chapter number 2 and just begin. We are already done with this segment. So I think most of these things can be skipped because we have created a Docker image and we are just using it. So you can skip all these things. This is applicable if you are not using Docker, which is not the case. So we can just skip. If you're doing on your own computer, which is not running Docker, and you want to do the hard way, this is how you do it. So it's not that hard. It is really hard, by the way, if you're on Windows. So I don't even bother setting it up on Windows, but this is instructions are provided for Macintosh and Linux. So you have to have these libraries, you have to get pip installed. And if you're using pip, you will use, of course, the what is called virtual env. That's a good thing to use. It's a great idea. You should use virtual env if you are using Python directly on a machine without Docker. But we are using Docker, so we can ignore all these things. You can keep moving. This is how you install various libraries: matplotlib, pandas, numpy, scikit-learn, and like that. We are also going to check the installation. So skip. Jupyter runs. We have it running already. And we can skip. Now we download the data. So the data is available in the location, which is what is that location. That's where the data is stored. And so we want to grab the data from there. So before we grab the data, we need to write a function to grab that data. And that is what we will be doing. So it's already written, by the way, here for us. So get the data function is written. Here is your fetch housing data function already written down, like here is right there. We have it already. We just need to go to that download route and grab the data. For that to succeed, we need to have a setup step. The setup step basically makes sure that you import the print function, Unicode literals, import NumPy, import operating system, put a random seed with 42 as an input, import matplotlib inline, and set some parameters for the axes, for labels that we will draw some graphs. We have a project root directory, we have a chapter identifier, we store our images that we will create using matplotlib in that location in the images directory, and we will define a function to save the picture. And we'll plot and save the picture in that location that we have saved in the images path, and we will ignore some warnings. So this setup needs to be run first. So let's go invoke that function. So our setup step, and invoke the setup. So now that setup is done correctly, we should just proceed forward with getting the data. Now, getting the data involves importing operating system, importing tar files, so we can unzip or untar the packet that gets downloaded. And from 6 moves, we are using a URL library to actually access this URL. And then we define a fetch housing data function, which is what is going to go to that URL and fetch the housing data in this step right here, which is what we are going to invoke. After we define the fetch function, we will invoke the fetch housing data using that function. We invoke it here. So let's go invoke this first, and this section, get the data section, and then we will fetch the data. So the data gets fetched. Now we need to, so that data is actually now sitting in our download route. That root location we have datasets housing.tgz is now available in our command line. If you then go and inspect your command line in Docker repository, for example, you should see that here. So if I may go to my location where the data is stored, and I will go there to the machine learning, hands-on machine learning, and in here you will find that we now have data sets stored in dataset housing.tgz. So here is dataset, then we go to dataset, and then we will and list, and we have housing. So go to housing, and then we have the housing.tgz. This one was just downloaded like a few seconds ago, October 2nd. The date right now is October 2nd at 17:44, and this was 17:43. So a minute ago, this was downloaded, as you can notice. we just ran that function right here, which downloaded this file into that folder in datasets housing.tgz. That location now has the latest data fetched from this location. So that's the source of our data. We have it now. Now, having understood that piece, we will now import pandas and create another function to load housing data in pandas. So we are using pandas to read the entire set of CSVs. So we have this housing.tgz file. We will expand that tar file and make it basically explode the tarball to get the CSV file in there, and then read that CSV in pandas. Now, for those of you who are new to pandas, what I would like to describe to you is the idea of why do we use pandas to begin with? Like, what's the benefit of using pandas like this and reading a CSV file? Why not just do it straight in Python? So that is the idea that I want to talk about a little bit here. So I will go to that sheet here and describe to you the idea of what is known as SIMD. And so before we talk about SIMD, let's go check what SIMD is. SIMD. So SIMD is this. It stands for single instruction, multiple data. And what this does is uses the CPU capability or the GPU capability. Hello browser. Here. Yeah, so what it's doing is SIMD is not the Scottish index of multiple deprivation. No, not that. The idea is single instruction, multiple data is a class of instructions available in modern CPUs and GPUs. Now, what are they really doing? It's like this. What you have is one instruction in the CPU or GPU that operates on the same concept or the same mathematical application of that instruction will be applied to multiple data points across a large collection of data points stored somewhere. Somewhere on the computer, basically. So you have it on the computer and you have one CPU instruction that executes SIMD, so SIMD instruction, and it will execute that typical specific instruction across a large number of data points, which is basically how you deal with vector operations. A large number of data points, you want to deal with all of them in one shot, you want to speed up the operation, and you do not want a for loop. For data point equal to 0 all the way through m, that is not what I want to go iterate on. No. That is boring and it is slow. That's why we want to use SIMD. And what SIMD instructions in modern compute CPUs and GPUs, what they do is essentially they will do that same instruction on multiple data at the same time in one shot SIMD. That's the idea. Now they have used SIMD under the hood in pandas, and multiple other libraries will actually take the benefit of SIMD in hardware, which is available in many processors. You can see that, Intel's MMX line all the way through the newest ones, MIPS instructions, IBM GPUs, modern GPUs are often wide SIMD implementations, 256-bit at a time. Intel's AVX SIMD instructions now processes 256 bits of data at once. So such are the CPUs available to us. If you look at some history and chronology, you will find it is not a new thing. People have been doing this for many years. You will also find that commercial software uses it, open source software uses these kind of capabilities, and that is where the underlying concept or the capability that I want to talk about is to use pandas. And what we are really doing is reading that data set from the CSV file here into a pandas array and returning that pandas array when we invoke the load housing data function here. That's when we will invoke it. But for right now, what we are doing is setting up that specific function itself. So we have fetched the housing data. We will now invoke this one and then invoke the number 5 here, in which we will actually call the load housing data function and then inspect the output. The output will be a pandas object right there. That's what I want to run next, is to actually load the data in a variable, a data frame it's called, in the housing data frame, and inspect the head of the data itself. That's what we will do in this step. So we'll just say shift enter, and what you see now is the head. This head is basically looking at the head of the data frame that you have in your handle. So you have the housing handle, and you're looking at the head, the initial few entries of data points in that frame, the data frame. And what you observe is you've got 0, 1, 2, 3, 4 are the indices. You have longitude, you have latitude, you have housing median age, you have total number of rooms, total of bedrooms, population, households, median income, median house value, ocean proximity are the characteristics, or also known as features of the data available to you now, loaded from this location onto a tar ball, expanded into a CSV, and read into a pandas data frame that looks like this from the first few entries in the data set, which is what you now have in a handle. We will now examine the information available in our handle, in our data frame. So let's go see. The next step is to check info about the data frame itself, which is basically producing the output that you see now, which I just executed, this number 6. And I see the pandas core frame data frame contains 20640 entries labeled from 0 to 20639. So there are data columns. There are a total of 10 columns, like this and this and this, like that. And those data columns, total of 10, include longitude, latitude, housing, total room, total bedroom, population, household, median income, median house value, ocean proximity, and that's what you have. Now you will notice that the data points should be 20640. You will notice that this number is not 20640. So we have some problem with the data right there. Here it should be full of information, but it is not absolutely full of all the data points. As you will notice, that is going to be one of the problems that we have to handle. So we don't have data right there. We have it here and here. So all the entries are appropriately filled up. But the total number of bedrooms data is not available for certain number of data points. We just don't have it, don't know what the value is. So now we can deal with it 3 different ways. One is to just ignore those data points, ignore. A second, put in a median value is one way. And the third way is to deal with 2 different methods of algorithms. One in which we will actually deal with total bedrooms, total BR, and we'll include that with the median values placed. And in the second iteration of another model, we will ignore the total bedroom count completely and see which one produces better results. So we'll do these kind of things on our own with understanding that we have a data point on total number of bedrooms. We don't have full data that we expected, which is what we find out now that we have info about the housing data frame that we accessed like this. So that is going to be a problem that we have to deal with. Another problem you will now see is that this idea of a ocean proximity is not available in form of distance from the ocean, which is to say that this is not a floating point number. This ocean proximity value is not floating point. It is not a number. It is an object, meaning they have assigned some ocean proximity labels as to how far or away are you from, or that area is from the ocean. And the labels are written like this. So if you just say housing ocean proximity value count, you will find out what types of objects are in that feature, which is ocean proximity feature. So we have various values here. Island, 5 data points are in the island, near bay, near the ocean, inland, and 1 hour from ocean. 1H ocean. That's how the labels are structured in this ocean proximity feature. And we don't have floating point values for actual distance from the ocean. And that is how the data that we have. So we just have to understand that we don't have such things that we might expect. Ocean proximity is not a number, but it's an object with these kind of values: 1H ocean, inland, near ocean, near bay, island, like that. And this is the data that we have. And that's our ocean proximity. Now, this will, will be a point that we have to handle and convert it into something that can be dealt with mathematically, as opposed to like leaving it like this, because you have to have a number and we have to do some math around it. So it doesn't readily adopt itself to a calculation, because it is more of a category than a calculation that we can do on a number. So if you now see that, I think I did not run these things. So let me run the housing info. So I run it. I see ocean proximity value counts, line number 7. I run it, and it becomes line number 8. I don't know, something is missing or what. Yeah, something is missing. See, number 6 is gone for some reason. Maybe, so ignore these numbers. They're not critical on the left side. Ignore the numbers. It's more of sequence of execution is important. So housing info, we got that. We got housing proximity count. So value counts, we got that also. And now we describe our data set. And what do we see is that we do receive the outcome that we see in terms of description versus info. What we see in the info is the actual columns described, like that. Whereas in describe, we see how many of them, the mean, standard deviation, minimum, 25 quartile, 50%, 75% quartile, and the max value. And that's the count you have. 20640 is repeatedly available. It's the same count, except in total bedrooms where the count is a little low. We understand already that, but we also have these parameters when we describe the housing data frame. We get mean, standard deviation, minimum. So now that we have the mean value for our total bedrooms as 537.87, maybe that value can be filled up in the remaining missing missing values that we don't have. Maybe we can fill up with the median value right there. So take this 537 and fill it up. That could be done as one approach. So next one, what we want to do is to just plot our data as we know in bins of 50 and in fig size of 2015, and just save the figure of this size. So we'll just save that figure and also see that figure right here in our notebook. So we'll just execute the describe function and then execute the matplotlib inline function, and it will actually save the figure and then show the figure to us. So it shows the figure. Now here, if you take a careful look at what figures we see now, we will see some of the characteristics. I should note that. So here you see from a visual perspective, the data is kind of skewed on that side, not here. Mostly it is empty. And so it is empty here. It says skewed in that direction, also skewed in that direction. Same here. That's an immediate observation. It's almost kind of sort of like that, but not really. The data is kind of distributed all over the map, but we see this unnecessary, arbitrary, I don't know what that thing is. And that is something that I cannot really explain to myself as to what this thing is. And so it suddenly bumps up to a very high number. What is that? Is something to wonder about. And that's what you visually see from a data perspective. So now we need to account for these facts that, most of the number of households in that data set that we have is kind of sort of limited in that range. And we don't have these values. So the data is, so this kind of a data where you have these kind of gaps in here, in here, and here, and here. These things are called skew. So we have to account for that and make it reduce the skew in a meaningful fashion. So we'll do that. And also, we have to understand what this thing is, because this looks like an aberration to me. Is that there is data points all over the map that kind of sort of like draws like this, but then oops. And so if you think about what this thing is, it's the median house value. And here also, you have some very old houses, the median house age. So we have age of the house is kind of structured like this. So there are new houses here, there are old houses here, and some of the houses are like really, really old. And that should actually show here on an extended graph, but apparently it is clubbed together, meaning the houses are capped at age 55 maybe. And every house that is older than that age is clubbed together in this point, is what this thing apparently sounds like to me, but we'll go and examine. Same thing here. We have these prices or the house values. And so we have houses that are 50,000, 500,000, $500,000. Is there no house at all that is more expensive than $500,000? That's not the case. We know there are multi-million houses in California, but then where are they located on the map, on the graph? Do we have them? Maybe here, but apparently the data has been squished, like compressed to fit into, and every house that is more expensive than this number, 500 million number, no, 500,000 number, is it 500,000? Yeah. So every house that is more than 500,000 is just stacked up right here. And that's the reason why apparently we have this kind of a view in the picture that we see. And that is what you should visually inspect your data to understand what is the data actually trying to show you. Or this is how you can actually infer that there's a skew apparently we need to account for. We need to have address these numbers that don't truly reflect what that data actually is, because this is actually wrong to have a $10 million house. Boom, you plot them here. That is a bad data. That is, we can actually visually conclude based on what we see here. So having seen these data points, what we want to go further is match this back to our notebook on one half, and this one on the other half. So let's review what if I'm missing something on the book itself. So that's what I want to make sure that I don't. And so we got a pandas data frame. We have a quick look. We saw our head. We saw our info. We saw our ocean proximity, and we noticed that this is not a value, but more of a label of various types. Now we also find out that the data here is missing for the total bedrooms that we saw already. And we want to make sure that we are accounting for those total number of bedroom count, and it is not this number which we want. And so we look at the standard STD row. We show the standard deviation, which measures how I think we already saw that in this picture in terms of standard deviation of the total bedrooms. The minimum number of rooms is 1, and the maximum number of rooms is maximum number of total bedrooms is like 6,400. That's also probably either a wrong data or something else. But that many rooms is kind of strange. Our mean value is 537 in a number of rooms in a district. That is the mean value. So which is what we want to fill it up with the missing data points that we have. Our standard deviation in minimum and 25%, 50%, they all look reasonable except the max values kind of out of the ordinary, which is what you also see in your total bedroom count. Where is that? Total bedrooms here. And so let's go see that picture a little bigger. And here we have our total bedrooms. Where did it go? Total bedrooms. There we go. That is total bedrooms. And we have 4,000 the max value. And so, yeah, it is just the count that is available. Apparently, from a picture perspective, it looks rational in that, you know, the graph itself doesn't show a large number like this, but more of a natural count of maximum, which may be, you know, one or two districts which may have lots of homes with lots of rooms, and that's the total bedroom count that you see is what you have. So it doesn't look out of the ordinary from a picture perspective. Having seen that, what we will, clear that. Having seen that, what we will now see is that in our histogram that we are looking at, if you see the same thing, that the picture also, the book also describes the same idea. What you notice, as I want to point out from here, is that the median income attribute here, the median income, which I think I missed in my look at the pictures themselves. If I go look at the median income one more time, and here we have our median incomes with where is the picture? Yeah, there. So let me reset this. And run this. And so it is going to produce that graph again for us. And here you will have, leave the page and open it up again, apparently. That's what I think I have to do. So I'm opening that page again and then go to that location. And here what you see is the idea of median income. So let's go see the median income page here. And you see that the median income values, if you look at the picture and try to understand what the message being communicated here in the median income, we see that the values are 2, 4, 6, 8. What's the unit here? We have no clear idea about the unit of measurement of median income in that district. And that is something that we have to account for very carefully. Otherwise, we will be confused about what that actually means. So that is the point that I think they're trying to communicate here, is that you will find out that this number 15 is an artificial cap on the median income. So the max value you see here is this blue dot, which is the number 15. Why did it jump like that? Okay. So here is your median income value. That blue dot shows 15, but that doesn't communicate anything. So once you find out what that actually stands for, is that the data has been scaled and capped at 15. That's why you see the number right there, here, this number, which is the median income. So in terms of what that actually translates to, is 15 is for higher median incomes, and at 0.5, the lowest possible number for income is a 0.5 as the lower median for income. And so the idea is to understand what the origins of the actual value of dollar numbers for incomes are, and they do not actually represent any specific unit as such. So we have to understand what that actually means. It's probably something like maybe 15 multiplied by 10,000, 100,000, I don't know. We'll find out what that means, but there is some multiplication factor that translates into a dollar median income for that particular district that we're dealing with. Now, the other idea behind housing age and housing value were also capped. You can see that those caps show up. Anything that is beyond a $500,000 home, the idea is that they have been capped like this, as you see in this 500,000 home picture, which is showing up here, the peak that you show. And same with median age of the home, which is this peak. That those peaks we already caught that visually. We need to understand that we want to handle that thing ourselves by removing the districts from the training set and also from the test set. So what we want to be able to do is, if you have a data point, these data points, we need to remove them because they don't belong and don't actually accurately represent our mainstream data that we have with us. Next, what we have is the scales of our attributes are very, very different. So we need to understand what is a scaling idea, that we will be able to account for them in a rational fashion as we go and discuss this. Another thing that we already noticed is some of these histograms are tail heavy, meaning that they extend much farther to the right on one direction. We saw that when I called the data being skewed, they extend to this direction all the way. You see that here also. The median happens to be somewhere in that location. And the data keeps on extending all the way is just what you notice. The number of households, same with population. The actual median is right here, somewhere in between that number. And so that's what you're noticing. And so we have to account for that by transforming these attributes to have a bell-shaped curve. We already know what a bell shape is. It looks more like this as opposed to a skewed shape like this, or a different skew that may look like this. So that's what we have to account for and make it more bell-shaped like by transforming the data set that we have in hand. And that transformation we will be able to do right here in our exercises as we go along. Now, before we proceed dealing with the data, it is a good idea to just set out a portion of our data set separately and mark it as a test set and put it aside. So we have 20640 number of data points that we have. So we'll calculate like 20% of these guys and set it aside as a test set and never look at it. Never. Until we are done with the whole thing. So take a portion of it, just keep it aside, because that's the only way for us to go back and test whether we actually did it right. Is our algorithm actually predicting the value? And we can test that with a test set, that we have to keep that separate. And so that is the idea behind creation of a test set. We'll do that next. So now in our illustration on the right side, we want to input a random seed, and then we will use NumPy to split, train, and test. We are basically creating this 20/80 split on the entirety of data set that we have and putting a set separate for testing. And that split of data is what we are really constructing. Now, when we try to split the data, we need to make sure that we are splitting the data across the board in a shuffled fashion. Shuffle. If you don't shuffle the data before you split, then you are skewing your data set in some unexpected way. So it is a good idea to shuffle. And that is where this random seed will come in handy for us to actually create a shuffled indices by NP random permutations of the length of the data. We are basically shuffling all the data sets in like we shuffle cards, pretty much like that, by using a random seed. And so to create a test set, what we are really going to do is shuffle, and then we set a test ratio, which is going to be in our case 20%, and create a test set and a train set. So whatever set we have, we'll call it out in two parts. 80% part, we call it our training set, and 20% part, we call it a test set. And we want to shuffle these things before we bifurcate them into two different parts. And that shuffling is what we will need to do right there. And this function will help us return a training and a test set. Basically, two different sets come back from the execution of this function after shuffling. And we are seeding this with a random seed with the value of 42 so that we run the same notebook over and over and over. We will absolutely receive the same exact random shuffle that we ran and got the very first time of the run. So I am going to execute this step to seed it with a random number and then execute the definition of this split train test function like that. And then I will use that split train test function in a subsequent step right there. And what I'm passing to it is the housing data frame that I have. And I also decide that I need 20% as my size of the test here. So that's the parameter I'm going to pass. It will be used as a test ratio because I'm passing it from here. And it will then come up with a output that is returned in form of a training set and a test set. That's what I'm returning. So that result will be assigned to a train set, and a test set is an outcome that comes from the split train test on the housing data frame with a 20/80 split. And when I execute this function, I receive a train set and a test set. So I'm going to print the length of the training set and the length of the test set. And that will show up like this. We'll just execute that and you get the output. Now what you are looking at right now is a, I am likely to get some noise because, oh, there is no noise. Great, thank you. The person who came in was about to ring a bell. And if that person rings the bell, then my dog will go and howl big time. That's a problem. It didn't happen. Thank you. So yeah, my dog is very quiet usually, but he sees some visitor, then he's going to make noise. And I saw the visitor and the visitor went away. That's a good thing. So back here, train and test that we are looking at, as we have a split already. So the training set contains 16,512 data points. The test set is now split in 4,128 points. So that's split 4128. We have those data points separately stored in a test set, and a train set contains 16512 data points already for us that we will now be focusing most of our energy right there. And we'll use this data to train a model. And that's what we now have handy. Now we will, what we want to do here in this is to, if you actually use this split again and again, what we want to be able to do is anytime we run this split, that we want to get the same exact data points that belong to the test set to stay in the test set and not have these data points show up here and some data points show up here. I don't want that mixing and matching to happen. I want on repeated runs of this notebook, I want that to exactly stay in the test group. I cannot really distinguish that, and we might see new data coming in and all these variables that we have to deal with. So we have to account for that. And that distinction between storing a test versus train set has to be done in a fashion that is repeatable. Otherwise, tomorrow you have new data and then you don't know what to do with it. So that is something that you have to account for. There are various ways to handle this segregation of split of test versus train, is to use the random seed like we discussed, and we ran it here, is one way. Another way you can do is that you can use some kind of a some kind of a checksum based method, which is CRC basically. So here is a CRC based method. I think that is also described here. So they're using CRC calculations and use that calculation to come up with a hash function that will split the data based on CRC value of the data itself. So let's see what that other method would be doing, is to calculate the CRC, or rather import the CRC function, and then test set check. We want to have an identifier and a test ratio. That's a function we are defining to check the test set. And here is another function we are defining, which is to split train test by identifier. So we have an ID column that we will be passing and using that to split the data set in test and train. So that split is what we are trying to implement, is another way of accomplishing the same idea. Now, the gotcha in this particular, I think they have defined, is if you have a Python 2 versus 3 implementation, which I don't think we have to worry about because our notebook already runs in Python 3, so that is not an issue. But you will likely run into, if you want an implementation that supports any hash function, here is one. So they're giving you an example of which hash function you want to use, whether irrespective of Python 2 or 3. And thereby you can now execute and inspect your test set head to see what values do you actually have in your test set. So we can quickly run through these and see what we have in our test set. So I'm just heading straight to the test set head to calculate the head, and we will notice what we get is we get an index 8, 10, 11, 8, 10, 11, 12, 13 are the indices that we have in our head of the test set. And that is, hold on, let me read this next block. It is just the inspection of the test set head. Next action here is to take the model that we want from scikit. We want to select a model, and from the scikit-learn library model selection, we are importing test train split. Now this is the scikit-learn method of splitting train and test. What they do is they will do whatever we attempted to do by hand by a random function or a CRC method. We will actually use the library to help us split train and test. So that is what we are really trying to import in scikit-learn. The model selection that we want to use, the function that we want to import is going to help us split between training and test. Those two sets, we will create that set, but use the scikit-learn method. That is why we are importing that model. And when we import that, and then we check for our test set head, we see that we actually do receive random identifiers right there. And we run that repeatedly, we will probably get the same random identifiers over and over again. If you don't use the scikit-learn method, you are getting 8, 10, 11, 12, 13, which doesn't look random to me or random enough to me from a test selection perspective. But this method of splitting train test using the library is actually producing the test set head, which seems random to me, is what you notice. If you go back and now attempt to draw a histogram of the median income on the housing data set that we have. So just focusing on the median income histogram, what you will notice is the same picture that we saw in the 9 of so graph that we saw early on, histogram graphs. We will see just one of them right now. And in here, what we want to be able to do is to make it more what I call bell-shaped curve. So what I'm trying to do is to divide by 1.5 to limit the number of income categories. And what that translates to, if you look at here. So from a visual perspective, if you see the median income, I'm going to divide by 1.5 to limit the number of income categories. All we are really trying to accomplish is income category as the original data frame that we have, which is the housing median income. So that this is the original data point. We are dividing it by 1.5, and thereby this data point here, which is at 15, will get divided and positioned at around 10. We are squeezing the data set by dividing it by a constant number like that. And when we have that, we will then label those that are above 5 as 5. What we are really trying to get to is labels that indicate anything above 5 is a high number. So we'll just put them all together. Let's see from a picture perspective what this is going to do for us. So if you look at this number here, 15, We are dividing it by 1.5. So these data points, all of these data points, by the way, will be shifting themselves to 15 becomes 10 and like that. So we are squeezing it. And then once we squeeze that, we will then categorize our income, median income as a category. That's what we want to be able to do so that we can then come up with a number 1, a number 2, number 3, 4, and 5. And anybody who is more than 5 after this division by 1.5, meaning anybody that belongs to 5 and higher, we will just put them together in one bucket, and that bucket is this bucket. And the reason we are doing that is we want to label all those that are above 5 as 5. So the idea is these are higher income group people, so high income. That's the underlying idea. Anything above 5 after this division, so in a 50% or higher income, you put them all together in a high income category. And then we draw a histogram of the income categories as opposed to income values. So early on in our picture here, we had median income, the value of income itself. Now we are coming up with a classification of income in these bucket points. We are now creating a classification because so here is a bucket, sorry, annotation. Here is a bucket, here is another, and these guys are all ones that are more than 50%. Before this division by 1.5, you can call it more than 7.5. After you divide, it becomes more than 5, and they all fit into this segment. So this is the categorization of our median income that we have done based on what you see here. The method of split between train and test, we use the scikit-learn method, which is the method that is a better method than doing it ourselves using a CRC based or other simply distributing as 80-20 split. That is something that you want to remember, that these libraries actually give you a automated method. Having said that, what we want to do is the reason why we create categories is that we want to make sure that median income is a very important attribute, and your experts that you tell that from your company tell you that you want to ask your experts, and experts are telling you to make categories of income as opposed to using actual numbers of income, because the expert knowledge in the domain of real estate tells you that people typically communicate and classify people with income into a small income, medium income, large income, or really high income. And that's the classification that people have been using. So experts tell you to classify as opposed to use absolute values of median income. And that is the reason why we modified and constructed this income category and attempted to label all those that are above 5 as 5, and then came up with these categorization of income, which looks like this picture that you see as plotted in a histogram for the income categories for the data set that you now have at hand. And that is, it is basically coming as an information from your discussion with experts who tell you that you want to make sure that you categorize the income as opposed to keeping them actual values. And since the median income is a continuous numeric attribute, you need to create a category attribute, which is what we just did here, income cat. And then use that to create these strata or stratification or classification. Now, each one of these strata that we were able to create that you saw, we divided it by 1.5, and primarily to limit the number of income categories. Otherwise, we'll have like so many of these. So we limited to only 5 of these categories. And then the categorization is then complete as we saw. So if you use 5 if more than 5, that I think is something that we have already accounted for, but I just want to make sure that I observe that. Where is this scenario? Is what I want to find out in our notebook, and it's right there. So the idea here is if it is less than 5, then you use it as is. If it is not, then you use the label 5.0 and make the modification in place. True. So the concept in this particular line is that you are looking at the income categorization, and if you find that the value of income category is less than 5, you keep it like that. If it is more than 5 or equal to 5, you make it 5 and update the data in place in the income cat segment in the housing data frame. And that's when you get these numbers corrected by this function. And that is where you see the housing income categories. Now, the underlying reason why experts tell you to do this kind of categorization is to make sure that we are eliminating sampling bias. And I'll tell you why it is relevant. I think we already discussed briefly what sampling bias was. As you saw that election from 1939 or whatever, Roosevelt versus somebody, the survey that was done to rich people who have access to telephone, who have access to subscriptions and club membership. But typically they are rich people, and as a result, Langley was projected to win, but he didn't, because your data was biased. And so what we want to be able to do is to not get biased in our data as we split into test and train. So there are subtleties that we are going through right now to help us understand how to avoid the bias, which is very, naturally creeps in if you don't pay attention to it. And that is what we are really after. So what we really want to do is eliminate this bias in salary or income category by shuffling and creating a shuffle that is a stratified shuffle. Now let's understand what that means by stratified shuffling. And this has practical implications to it. So I'll elaborate a little bit on, excuse me. I'll elaborate a little bit on what this stratified shuffling is and why it is relevant. It may not be intuitive in the book or the exercises itself. So the underlying idea is like this. Here. And go to the other sheet. Where is the other sheet? Right there. Hello. Yeah. No. Clear the drawing and go away. Yes. You. Show me. Yeah. So the idea that we want to do is a stratified shuffle, not simply shuffle. That is the concept I want to describe. If you take a bunch of things, let's say, if you have 5 little pieces of paper, let's call them A, B, C, D, E, and you want to shuffle them, it's easy to shuffle, just randomly shuffle them around, no problem. However, if I now tell you information about the fact that, A and B are really, really poor, and these guys are rich. I just tell you that there are 5 different things. 2 are poor, 3 are rich. Now you want to take a shuffled split, and you can do that very easily. Just take 20% of this, so you get 1 as a test case, right? So maybe this is too small a number. 5 is too small, so just take a larger number. But just giving you a representation of this. So you take a 20% of the data that you have, and you get some poor and some rich. However, we want to have, if you notice in this data set, not just 5, but a large number, you'll see that about 2 out of 5 are poor and about 3 out of 5 are rich people. And so what you want to actually do in case of a stratified shuffle is you want to divide your data into 2 parts, your test versus train data. The train data needs to get 80%. Test data needs to have 20%. But you want to make sure that your ratio of rich versus poor in here, as well as the ratio of rich versus poor in here, is also the same. 3 out of 5, 2 out of 5, 3 out of 5, 2 out of 5. And that may not be directly, readily possible by purely random shuffling. And that is the underlying reason why we want to make sure that we eliminate any such sampling bias by shuffling them in each of those strata. We have a poor strata and we have a rich strata. So we want to take 20% from here and 80% from here and put this in the train and this in the test. And same here, we have strata 20%, put them in a test, and 80% put them in train set, so that in the final test and train split that we have, we are getting the strata of the society, as opposed to just grabbing a random shuffle, which might introduce sample bias or the bias that we don't want in our end result, in our test train split. And that is the underlying philosophical thinking behind why we just did this, which is to create income categories. Because what I really want to get to is I want to get our test train split in a stratified sample, as opposed to, or a stratified shuffle, as opposed to just pure shuffle. And I want to stratify based on the income categorization that I have just created by this math. Divide by 1.5 and create categories. If it is more than 5, then you just label them as 5, and these are the strata of the society that we now have. These are the strata, 1, 2, 3, 4, 5, 5 different societal divisions on income categories. And I will use these as my stratified shuffle. And there is a method to do that in scikit-learn. We'll just see that now back here. And so now that we have income category as a new created attribute, which is derived from median income itself, we will use that as a shuffle based, we use that as a stratification to help us shuffle properly. The underlying idea here is we will use scikit-learn library and a stratified shuffle split. Now this needs the input of income category right there. So we now want to create the test train split one more time, basically do the shuffle one more time, but this time our shuffling is stratified shuffle as opposed to just shuffle. Just shuffle can lead to bias. And that is the reason why I want to avoid that bias, is by creating a stratified shuffle. I hope that is clear. If not, just stop me and I'll clarify. But now if you look at this picture, what you're now looking at is essentially this train index and test index. What we are really running through is a for loop, train index and test index in a split of housing data frame based on income categories. So we are splitting them into categories, and then we have a stratified training set and a stratified test set, and that's what we will be using. And when we invoke this function or this particular cell, we have an error because apparently I missed out on a previous step. Okay, let's go back a step to this. So we execute again, and we get a median histogram. Then we have a housing income category values calculated, and then we run the stratified shuffle split. And now we have it, where you can now count the test set and calculate its length. And same with our income category value counts. What you're now looking at is the stratified test set value counts divided by length of the stratified test set. So this is what you're looking at, which is the same numbers that we saw before here, except we are dividing that with the length of the test set itself. And in here in the entire housing data set, as opposed to just the test portion of it, we are doing the same math, but for the entirety of the data frame, housing data set or data frame, based on income categories, count the number of values, and divide by the length of the entire data frame. You will see similar patterns. And what you see is this number 3, which is the classification of income categories, 0.35, which is kind of sort of similar to this number. You will see the number 5, 0.11, which is kind of similar to this classification. And what we are really trying to find is our test set a true representation of the overall data set, the housing data frame that we have. So the way we did this calculation versus that calculation is to give us a strong sense of belief that our test set actually represents the overall housing data set itself, as opposed to a skewed non-stratified shuffle. If you do a non-stratified shuffle, you will see that these values will not align. You have a 0.35 here and a 0.35 here. That is a good alignment. For the category number 2, housing income category number 2, is the number that we have is 0.31, which is what we are really calculating. If you look at the values here are actually what I will call income category proportions of the category itself. So a proportion here is basically means 35% of the overall data set belong in the third category of income. And here, if we read this number, it will basically translate to the same idea, which is 35% of the overall proportion of the test set belong to the third income category. That's how you read it. So if you scroll down to this number and compare it with that number, the numbers are similar again. It reads something like this, that in the first income category, the total proportion of people with that income is about 3.4%. And that is how you would read this number, is the total number of people in one or the first income category in our test set is also approximately 3.9%, is what you would read as a proportion of the overall test set, is how you read these numbers. And this is where you will be able to get a good sense whether your test set that you have derived from the overall data set is actually a stratified shuffle based on income category or not. That's the core idea under the hood. Any questions at this time are welcome always, of course, and questions are welcome anytime. So let's go keep going further. What we are really trying to find out now is once that we have these proportions of categories, let us see if we can compare our proportions across the board. So what we are really doing now is to make sure that we are indeed avoiding any bias, is what the ultimate goal is. And we want to find out the comparison between when you do a stratified sample versus versus a purely random sample. Let's see what the differences are in the two approaches in when we actually take a stratified shuffle as opposed to a purely random shuffle. So those two we will do in our next idea here, which is we want to define a function which is called income category proportions, which basically returns the data for income category and its value count divided by the length of the data. Basically, these kind of numbers that we already have calculated in the past, in the previous example. That's what we will return in this income category proportions for a given data set. That function will return the data corresponding to something like this, the proportion of that category for that income category itself. That function having been defined, that function, we will now test, so train and test, make a test train split purely using random. And the random that we are using is 42. The seed that we are using is 42. That's the random generation of test and strain, and we are splitting that. And that is one way of splitting. The other split we will be doing is our stratified sampling, right? So we'll then compare the two. So here what we have is compare our proportions on the pandas data frame for overall, for stratified, and a purely random sampling. And so those three is what we want to be able to compare. And so the comparison results show up like that. Let's go see the comparisons. We'll execute the comparisons also. And what we see now is the overall data set has about 3.9% for the first income category, 31% for the second, 35% for the third, and like that. That's the overall proportions of categories of income in the entirety of data set. That's what we have here. If you then look at the random split, that random test train split using a simple seed, what you see is that the data for the first income category is in the ballpark, but the other ones are not so much. They are deviating a little bit away from what we expect. Whereas the stratified sampling results are more closely aligned to the overall sampling, the overall data set. So just compare these numbers with these numbers, they better align with each other compared to a randomized split of test and train. And that is, I think, a key thing to remember and understand. This is not super obvious, but you need to understand like how do you classify your data and how do you then divide a test train split. We are not even into applying a machine learning yet. We just want to take a step back and understand how do you actually carve out a portion of data into a test set that we will then come back and look later on to measure the accuracy of whatever model we will fit and see if the model that we fit actually comes up with a correct prediction on a test case, because that will be a very good indicator of what the future will entail when we will put our model in production. And further metrics that we want to look at is random error and a stratified sampling error, so stratified shuffle error here. So the stratified shuffle errors are low, as you can see, compared to the random shuffle and its test strain split. The numbers of percent of error as it calculates is a little bit high. And we want to minimize our error function. And we want to reduce the error in comparison between what the overall numbers are versus what the test strain split looks like. And therefore, it makes a solid sense to listen to the experts that were telling us before already, is that you want to ensure that the test set is representative of the various categories of income in the whole data set. That's what the experts tell us. You chat with the experts and the experts tell you that whatever split you make, that you want to make sure that the income as a category should be accounted for. And that's the underlying premise that we want to go about in all the way up on top here. When we went ahead and took the income itself, then we came up with a way to compress it, create buckets around it, and created these 5 buckets or income categories. We use those categories to then create stratified shuffle split, and that we used a scikit-learn model. Scikit-learn has a library built-in function for that expects an income categorization as a parameter that will split it for us. Then we validated that our stratified shuffle split has smaller errors as it compares to the overall dataset population compared to a random test train split. Okay, now that we have this clear idea that our test train split is done better when we are using a stratified sampling method, because these errors that we know are low compared between stratified and overall. So we want to use that approach. And so what we want to do is we want to remove the income categorization, because it is something that we created purely for the purpose of creating a test train split in a system which does not have a bias based on incorrect or purely random shuffling. So we did a stratified shuffle, and now that we have accomplished that goal, our need for the income category attribute, which was an artificial attribute we created up ahead here. We created it where? Yeah, I think somewhere here. Yeah, here, that's where we created, and that we don't need it anymore. So when we don't need it, we want to drop it. And that's what the idea here in this segment is, to just drop like that. So we drop that particular income category as an axis and modify our data set, because we don't need it anymore. We don't need the categorization. We have our test train split in hand, and that's a good thing. So we'll use that. Now we will go further. And what we just did was that we have generated a test set. We're keeping it aside separately, not touching it, because it should not be touched until the entire exercise is over. Then we go and test. What did we do? And now that we have done this split, we will now have a way to cross-validate, and we'll discuss and find out ways to validate when we have our model as we go and build it. Next, let's check time quickly, how much we have. It's already 7 o'clock. We have 9 minutes. So let's see how much we can actually cover today, because this is a net new idea. So let's see how much we can actually meaningfully cover. So the discover and maybe visualization aspects we can go through and understand as to what. Let's see how it plays out, how much time it actually takes. So the idea behind a discover and visualization of data to gain insights. I think we should be able to finish that today. So we want to now go into our training data, not the test data. We're not touching it. So we are going to create a copy. So stratified train set that we have created, we create a copy. And that's the housing label actually now is going to point to that. And so this housing variable is a data frame that maps to our stratified shuffled training set, creating a copy of that. Now that we have in hand, we will plot it and see what it looks like from a X, Y scatter plot. And we know we have latitude, longitude in place inside the data structure. So we'll use that as our visualization. And we just call it a bad visualization plot. And we just plot it. So this is how it looks like. And it saves a bad figure. What you now have is something that kind of sort of looks like California, if you will, but not really. So because it doesn't convey anything quite yet. So what we want to do is, improve upon the visualization of this picture, because what we want to be able to do is insert what is known as an alpha index in a graph. This alpha index essentially is a measure of intensity of a point on a graph. So if there are too many points, it will of course make it a deep blue versus a light blue. So this alpha is, think of it as a transparency metric in a picture. And so if you insert that alpha in a housing plot and save a better visualization plot, you get a better visualization plot, which actually gives you a little bit of semblance of what that dot is here and here versus these guys are dense. So that density is not very clear in this bad visualization plot, whereas it is kind of sort of apparent that these areas are dense and these are not so dense areas, and very, very sparse here and here and here and maybe here. like that. So that density or metric can be captured visually by inserting an alpha metric, which is basically, think of it as transparency in a picture, or alpha transparency, or there's a word for it. There's a better word for it. I'm trying to remember. So what this thing called is graphical illustrations, but I'm forgetting that. Okay, let's keep going forward. What we are now looking at is putting in color to it. So this color valuation or the color representation we'll use the idea of color in the median house value. So that house valuation itself will put in different colors, and that is a built-in library function called jet. So that jet thing is a plotting function that automatically creates color plots. That is, I think it's a library function in matplotlib. And so what we are really doing is using our median house value as the index to show different colors to different values. And now you have a result that not only has an alpha value, which shows you density function, but also has X, Y, latitude, longitude, has labels of population, and the median value of the house actually shows in a color plot. So the more expensive houses are kind of reddish and yellowish in color compared to the cheap houses are light bluish and bluish in color. So all over the map. So the whole spectrum shows you in a picture, which is a scatter plot, better drawn visually, inserted with information that indicates price of the home embedded in the colored picture itself. Next, what we want to be able to do is, let me see if I'm missing something here. So I think not. Yeah, I think we want to insert an idea of proximity. And so that I think I already mentioned to you about the jet function, which is built into the matplotlib library, which we have used already. And what we want to now do is to measure proximity to cluster center. Clustering will detect clusters. So the idea behind the next idea is to find out if we can apply a clustering technique to detect clusters of houses which are closer together. So that might give us some population density information already. We can actually tell that already visually by just looks of the graph here. But let's go read this piece that I did not go over, which is to import matplotlib image as mpimg and then California end-to-end project. We are creating a scatter plot with latitude, longitude, housing population. So it's the same thing, except our color bar is also using jet. Then we are plotting prices. So I think it is merely putting the latitude, longitude labels, a median house value label, and save this picture in a font size and show the picture. And that's the metric I think that we have inserted compared to the earlier picture is that we have, I think these colors here and the color here is what shows up, is what I see is different. It's more of a cosmetic representation than anything else right now. But let's go execute that piece. And then the next one is to create a correlation matrix that I want to find out for the data frame that we're dealing with in our training set. And so we will then find out what that correlation matrix evaluates to in the next step. And what you see is if you sort them in a increasing order, or rather not increasing, ascending false, so decreasing order, you will notice the median house value correlated to the median house value itself as a perfectly correlated to 1. And what we are really trying to do is a correlation of various features with the median house value and trying to understand which metrics or which features actually positively correlate to the median house value and which negatively correlates or which do not matter much. The reason why we are calculating these metrics, or rather correlation measurements, is to understand the relative importance of various features. For example, this particular feature called total bedrooms has a very low correlation with the actual median house value, 0.04. The population also is a low number, 0.02, negative. So if there is more population, the price, the median value of the home is actually slightly less. That's a negative correlation. Similarly here, the latitude has a negative correlation to the median house value. What does it indicate? That latitude being a negative correlation with the house value. So practically it means kind of sort of that the houses in the northern part of California are cheaper. That's what it basically means. This number kind of sort of hints towards that, because what you're looking at is a latitude number, negative correlation with the median house value, which indicates that if you increase the latitude, which means you go south on the map, that you are likely to see higher prices, higher median value of the home. The longitude, meaning going east to west, doesn't seem to impact too much, at least a tiny little bit much. Not really too much. It's not too much impact right there. This has some impact. 0.14 is the correlation negative to the median house value. The most important attribute that actually impacts the median house value happens to be the median income in the district that we're dealing with. So the median income, if it is high, it is very likely that the median house value in the district is also going to be high. I think that's a very, very rational conclusion we can make from this data point. Based on just what you see in the correlation matrix itself, is that if you have people with higher incomes, it is very likely that the homes in that area will be expensive. And that is what you actually see right there. If a house has more rooms, it has some implication to the median house value. It's a bigger house, it's a bigger price. Total housing median age, so sorry, it's not total, it's just housing median age has, about 0.11, so it's not a 0.11, 0.11 correlation with the actual house. So that's what you read from these. So that gives you a semblance of a correlation between the actual features of the home compared to the median house value of that particular district. We can plot these things and understand how the scatter looks like from a picture perspective. What we just saw, it will show us visually how these things actually impact. So what we are going to do is plot a scatter matrix, and we will use the attributes that show us median house value, median income, total number of rooms, and median age of the housing median age. And we'll draw that scatter matrix, and we have chosen only these attributes, and we are going to create a scatter matrix and plot it out to see what pops up. And what you see here is let's go execute that first. And so it is going to generate. Did I execute that? Not yet. So maybe I execute. No, I think it came back. So what we are now looking at is it's basically a 4x4 matrix of graphs. So 4 on the horizontal side, 4 on the vertical side. And there are 4 attributes we are really handling here. So median house value, median income, total rooms, and median house age. Those are the 4 metrics or 4 attributes that we have in our hand. And we are trying to see this chart, for example. It represents median house value compared to median house value. So it is not going to be very informative in its nature because the correlation is 1. Median house value with median house value is 1. Similarly, this chart is comparing median income with median income. So this chart is going to be a correlation of 1. So it doesn't show any scatter. Same with this. Total rooms, doesn't show any scatter, and housing median age, no scatter. So on the axis of the matrix, or the diagonal, of main diagonal of the matrix, you will see no scatter because there is none. It is comparing with itself. So that's why you don't see any scatter. But in all other charts, in the upper triangle or the lower triangle, you see scatter. And this scatter is what is a visual representation of what you saw in, say, for example, these four metrics. So we have housing value, median income, total rooms, and housing median age. We have taken only these four, and what you see in these numbers here, 68 and 13 and 11, is what is represented in the same idea represented in these pictures, which show you a scatter of how median income in this picture, for example. So let me double click. Yeah. In this picture, for example, what you're looking at is a scatter plot between median house value compared to median income. So if you have more income, the house values are going to be going higher. As a consequence, what you notice is the aberration that we saw before is that if you have median income versus median house value, you see that this line here is the aberration we see in exorbitantly high housing values. They are all clubbed together to some number, 500,000, 500K. That number, all the houses that are higher than that price are somehow clubbed there. So no matter what median income is, that is showing you as a scatter spread out, because it's actually bad data that should be addressed. So we'll address that at subsequent time. I think we crossed our limit. So we'll resume this, and we'll keep going, understanding our concepts as we build this entire pipeline of data as we develop our model, and then we'll go back and test it. There are lots of subtleties that do not directly involve straight jumping into running an algorithm, because that is actually trivially simple, as you will see subsequently along down the chain. Running the algorithm itself is like one line of code, and that's not the biggest stumbling block, but that's not the crux of the problem. The crux of the problem is to understand the data, reduce your bias, find out what model will fit the best based on mathematical calculations that actually look at error functions, minimize the error function to a value, and that will generate your ideal model. Then you have that model ready, you go back and measure it with the test data that you have preserved already. And by the way, your test you created is a stratified sample of stratified random sample of 20% set aside. You use that data now to validate your model, and then you will feel somewhat level of confidence whether the model you have come up with actually validates against your test set. And when you feel that level of comfort, you can attempt to go into production and see if it actually performs, how well it performs with real data that you will get in the future. And with that, I will stop recording. And I'm open for questions. Questions are welcome anytime. I know some of you are away. And so I'm stopping to record.